So recently I had this interview with a flat earther called Mark Doxey.
I had a bias towards anarchy, and here's Eric Dubay being interviewed. So that was the start.
Now, if I've timed this right, that video has just been released at the same time as this video and is linked in the description. And in that interview with Mark, I asked him to present me with 3 pieces of evidence for flat earth. And I promised him that I would make this response video and I would answer all 3 pieces of evidence. After this video, Mark will be allowed back on my channel to let me know what he thinks. So let's begin. Evidence number 1. These pictures here. So Mark started off by showing us these 2 photographs here of the CN Tower in Toronto. The one on the left was taken from a distance of about 32 miles and the one on the right obviously much closer. Now, as a reference point, we both agreed that these 2 buildings here were exactly the same building, as were these 2 buildings here, and these little groups of buildings in the green circles are also the same. Now, normally these types of photographs would be used as evidence of curvature of the earth due to the obstruction that we can see in the picture on the left hand side. Although Mark seems to think that something else is at play, some sort of optical effect or optical illusion. So let's hear what his problem is. So Mark has got 3 main points that he wants to make about these photographs, and you can hear them explained in full in the interview that's linked in the description. But for now, let's summarise the first point.
And what's this space here? Now, the image on the right has got lots of buildings that sort of average out, and the tippy tops of them can be seen on the distant photograph. But on this one, on the more accurate picture, the closer one, there's an even height, but there's a gap in the distant one where that bracket is. What accounts for that?
Now, there is a bit of a standing joke in the flat earth community that the word perspective is the answer to everything. But I think in this case, perspective and a bit of parallax genuinely do answer our question. Let's see what I mean. So here's a picture of the Toronto skyline, and we can see that as we move our position just ever so slightly, that skyline appears to drastically change. Just like with these 2 photographs you see on the screen, they have definitely been taken from different distances, but they've also been taken from slightly different viewpoints. The much closer photograph on the right hand side has been taken from an angle similar to this one. However, the more distant photograph has been taken from a more side-on view like this. So Mark, I know at this point you're going to be thinking, do I actually have anything that's going to back up that assertion? So let's use our old friend Google Earth, and let's see if Google Earth, which remember is based on a globe, if Google Earth will actually predict what we see in these photographs. Well, this is a screen grab from Google Earth from what I believe is the angle that the more distant photograph was taken from. Now, the picture on the left here has been taken with a zoom lens camera, but Google Earth doesn't offer that feature. In fact, if I zoom out any more than 7 or 8 miles on Google Earth from the Toronto skyline, the resolution becomes that poor that it's very difficult to pick out any sort of individual building. So what does that mean? Well, to put it simply, in that picture we are starting to see signs of obstruction due to curvature of the earth. But because that picture was shown from about 8 miles away, we're not going to see anything like the obstruction that we would have seen from 32 miles away, which is a distance that the photograph was taken. But what if we artificially added that obstruction? What would we see then? Well, this is what we'd see. Google Earth clearly predicting that gap which we can see in the original photograph. So I think that shows that the gap that you pointed out that you didn't think was possible really was just a byproduct of the angle that the photograph was taken from. But just to clear up any doubt, do you remember that building that had the antenna on the top? Well, you might be wondering where it is on this picture of the skyline, and that might lead you to believe I'm trying to pull a bit of a fast one, but this is just another example of when you come too far away from the skyline on Google Earth, you lose a lot of resolution. So let me zoom in and we'll find that building for you. So I'll just highlight with my mouse. This is the building there that we're going to zoom in on. Still can't see the antenna, still can't see it. That's the building, but in about 3, 2, 1, it's the BMO Bank. There you go. There's your antenna. Same building. So issue number 1 addressed. The appearance of that gap was just to do with the change in the angle that we took the photograph from. So what was Mark's second point?
Now on the left there's another building, which was this one here. But where is it? On the right. It's not there.
So it does appear that in that photograph on the right a building has vanished, but really the reason for this is no different to the reason we've just discussed for point 1. So the building he's talking about is this one here, and it does seem to be missing from the second photograph. But when we zoom into this photograph, the reason why quickly becomes pretty obvious. It is just shorter than the buildings around it. So if we were to zoom out a little bit and then turn to the angle that the closer photograph was taken from, it would simply just be hidden by the rest of the skyline. But there was also a third problem with these photographs, and again, I'll let Mark explain.
So we've got the CN tower. The line goes over the white building, which is the one that we were questioning. Where's it gone? And the next high building is slightly smaller. Slightly, is it 5 stories difference or 10 story? But it's smaller but identifiable. Now on the distant one, again, if we put a line from that identifiable building to the left, why have those buildings got so small on the left hand side of the CN tower compared to the right hand side? If this was curved, the same effect would happen uniformly right from the left to the right.
So again, I really do believe that this is caused by the angle that we took the photograph from. But rather than take my word for it, can Google Earth predict the same observations? So this screenshot was taken from a similar angle to the closer of those two photographs. And we can see from this angle that that building on the right hand side does indeed look to be just a little bit taller than some of those buildings on the left. But if we then go to the angle that the more distant photograph was taken from and zoom in and add a little bit of Earth curvature, we can see that difference looks even bigger. But then we have to remember that even this screenshot was only taken 7 or 8 miles out. If we were to add the Earth curvature we'd expect from about 32 miles out, we might see something like this. And now it looks like it's absolutely towering above any of those buildings on the left. Now, just to finalise that point, I obviously don't know the exact locations that these two photographs were taken from, but if I did, I'd be able to get a far, far better replication using Google Earth than I've managed to. But I think even with the just 10 minutes that I spent faffing around on Google Earth, I've shown that these photographs are absolutely possible. So in short, I really don't think that there's any issues with those photographs at all. I think that has been cleared up. So let's have a look at point number 2. Evidence number 2, flight times. Now again, you can hear Mark's explanation on this in full in the interview linked in the description, but it boils down to this.
Biggest a proof, maybe if anybody can correct me, it's the east-west takeoff getting from Europe to America, America to Europe. Once you've got an engine, you separate yourself from the rotation of the Earth, and so you should be able to get there faster one way, a lot faster one way than the other way.
Okay, so it's a fairly understandable question. Why are flight times flying west not shorter than flight times flying east? And there was also another specific bit of criteria that you wanted addressing.
If you could just separate the car on the Earth, fastened to it, compared to an engine in the atmosphere, that would be the criteria for me.
So I've thought really long and hard about the best way that I can possibly explain this, because it is a very counterintuitive argument. I mean, if the Earth is rotating west to east, intuition tells us that it should be faster to fly west than to fly east, and that's not what we see. So what I've tried to do is start from a starting point that isn't counterintuitive. Start from a starting point that we can both agree on. Now, you've got to forgive me if the start of this explanation seems a bit low level. My intention is not to patronise anybody. I think it's just important to start from a point that we can all relate to. And to do that, I'm going to start by ignoring the atmosphere. Now, I will get there, I promise. I'm not trying to strawman you. All right, I will get to the atmosphere, but we're going to start off by ignoring it, and we're going to imagine that we're sat on this train. Now, at this point, I want to pause the video just to say, can we all please admire my PowerPoint skills, please? Now, that train is travelling at 100 miles an hour, and on the train, I've put a toy plane. So my first question to you, very intuitive, is going to be, how fast is the plane travelling? And I don't think anybody watching is going to give an answer other than 100 miles per hour. Obviously, we're talking relative to the Earth, but I don't think anybody's going to argue that that plane is travelling at the same speed as a train, 100 miles an hour. Okay, so far so good. Now, what would happen if I took that plane and threw it straight up in the air? What would that plane do? What matches our everyday observations? Well, what matches our everyday observations is that that plane would go straight up and down relative to the train. It wouldn't fly to the back of the train or the front of the train. It would just go straight up and down. Yeah, if we're sat on a train and we throw a ball up in the air, if we throw it straight up, it's going to go up and then come and land back in our hand again. And I don't think I've said anything that we disagree on. I think that matches what we'd expect. We'd throw the plane straight up and it will come straight back down again. We could call it conservation of momentum, blah, blah, blah. But really, all we need to know is that that plane is still going to be travelling left to right at 100 miles an hour. So let's just take it up a notch a little bit. This time we're going to throw the plane forward. But the person throwing the plane forward is going to throw it at 10 miles per hour. Now, how fast is that plane actually travelling? Is it travelling at 10 miles per hour? Or is it travelling at 110 miles per hour? And this is another point I don't think we're going to disagree on. I don't think anyone's going to disagree that relative to the train, that plane is travelling at 10 miles per hour. But relative to the Earth, it's travelling at 110 miles per hour. But what if I threw it backwards across the train? What if I threw it at 10 miles per hour backwards? How fast is that plane travelling now? Is it actually travelling to the left at 10 miles per hour? Or is it still travelling to the right at 90 miles per hour? Which will give it, relative to the train, a velocity of 10 miles per hour to the left. So I think here the plane is still clearly moving to the right, but it's just moving to the right now at 90 miles per hour rather than 100 miles an hour. You see, it doesn't matter whether I throw it left or whether I throw it right. It will move relative to the train at the speed that I'm throwing it at, but not relative to the Earth. So if you were on this train and you decided to walk from the back of the train to the front of the train at 10 miles per hour, it would take you exactly the same time as it would to walk from the front of the train to the back of the train at 10 miles per hour. And that's because you didn't start off not moving. You started off moving at exactly the same speed as the train. And if you want to detach yourself from the friction of your feet against the train floor, imagine throwing a ball across the train. It wouldn't matter if you threw the ball from the back of the train to the front, or whether you threw the ball from the front of the train to the back. As long as you threw it with the same power, it would take exactly the same amount of time to travel exactly the same distance. And that is because that ball didn't start off not moving relative to the train. That ball started off moving, just like our toy plane, at exactly the same speed as the train. So I know I've not mentioned the atmosphere yet, and I will get there, but for now, just pretending the atmosphere doesn't exist, there is no difference between the plane on the train and a plane on the Earth. When the plane on the Earth flies west, it is actually still moving east, just at a slower speed than the Earth beneath it is rotating. It's exactly the same as when we threw that plane backwards on the train. So it really shouldn't make any difference whether we fly west or whether we fly east. I do just want to point out that because we have a slower rotation at the poles, if you are close enough to the poles, then you can actually genuinely fly west. But that's the exception, not the rule. But let's very quickly just think about flight times on a flat Earth. The orange circle in the middle represents the northern hemisphere and the yellow one represents the southern hemisphere. Now, it doesn't take a lot to see that in the southern hemisphere, planes either A, have to fly far, far, far faster than planes in the northern hemisphere, or flight times are going to be far, far longer because of the increased distance they've got to travel. But that just is not what we see. We do not see flight times in the southern hemisphere being hugely longer than flight times in the northern hemisphere. We don't see anything like that. So now we've shown why that without an atmosphere, flight times travelling east should be exactly the same as flight times travelling west. Let's add the atmosphere. And to do that, we're going to take a look at this swimming pool. If the water in this swimming pool was still, then walking in one direction through the swimming pool should take you the same time as walking backwards in the opposite direction. But of course, if that water was flowing in one direction, then it would take you longer to walk across that swimming pool in one direction than it would the other. And it's the same with a plane. A plane flying into the wind is going to be taking longer than a plane that's flying with the wind behind it. Now, because the Earth spins from west to east, the atmosphere also spins from west to east. And it's for this reason that flight times are counterintuitive. You see, the average flight time from Los Angeles to New York, travelling east, is 5 hours 15 minutes. Because we've got the wind with the plane. However, if we try and fly west in the opposite direction against that headwind, the average flight time is now 6 hours and 30 minutes. So we do get exactly the opposite of what we would expect if we just used intuition alone. But of course, this is the wind and weather systems, and it's going to get even more complicated. You see, when slower moving Earth from the poles starts to drift towards the equator, the Earth underneath it is now spinning faster, so the Earth appears to drift west as the Earth overtakes it. And as the faster moving Earth from the equator starts to drift towards the poles, it starts to appear to drift eastwards because it's moving faster than the Earth beneath it. Now, we all know this as the Coriolis effect, and the effect it has on flight times changes with the seasons and with latitude. So, all in all, flight times, they are hugely complex, but the complexity comes from the movement of the atmosphere and not the rotation of the Earth. So, as counterintuitive as it first may seem, there really is no reason whatsoever why flight times travelling west should be any faster at all than flight times travelling east. Let's have a look at your piece of evidence number 3. Evidence number 3, feeling the spin of the Earth. Okay, let's see what Mark's got to say about this one.
Miles per hour is a different concept to rotation per day.
Yes, it is, yeah.
Yeah, so you and I are travelling at 700 miles per hour on the surface of the globe. Now, at 6 o'clock in the morning, the Earth is pushing us at 66,000 miles an hour. 12 hours later, the Earth is pulling us, you and me, at 66,000 miles an hour. So within 6 hours, the Earth is pushing us at a massive speed, and then it's pulling us at a massive speed, and we don't feel it.
So again, this is quite a counterintuitive point. You know, intuition is going to tell us that if we are on a ball and we are spinning at these huge speeds, then we should be able to feel it. So let's start the explanation again at a point that I think we can both agree on. And that point is starting here. This red dot is going to travel around that circle in a clockwise direction. Now, if we were to take an instantaneous snapshot of its motion at that point, let's say it's traveling at 10 meters per second. At that point, all of that movement is in the horizontal direction. It is traveling at what we'd call a linear speed at 10 meters per second to the right in that horizontal plane. There is absolutely no movement in that instance in a vertical plane. It's not moving downwards at all, it's moving just to the right. Now, a little while later, that situation has been reversed. While that red dot is now here, at that instantaneous point in time, all that movement is in the vertical direction. All that movement in the horizontal direction has been lost. So we can look at this in two different ways. We can say that there's been an acceleration in the vertical direction. We've gone from no meters per second to 10 meters per second in that vertical direction. Or we could look at it from the other point of view and say that there's been a deceleration in that horizontal direction. We were traveling at 10 meters per second horizontally, and now we're not traveling horizontally at all. Now, we know from Newton's laws of motion that whenever we have an acceleration, we have to have a force. And we might learn that at school as force equals mass times acceleration. But this equation here can be derived from force equals mass times acceleration. This will tell us the force that we feel when we're moving in a circle, when those changes of speed in the x and y direction are taking place. And I think that anyone who's ever been on a roundabout is going to agree that, yeah, you can totally feel that force when you are spinning in a circle. But the point I want to make here is that that force happens at every single instance of a circle. We can't treat it as the top of a circle going one way and the bottom of a circle going another way. That force, that acceleration is being applied at every single point. Every single instantaneous point on that circle, we are feeling exactly the same force. And the reason I say that is I want to get away from this idea that if we're traveling in this direction here, we are somehow receiving a massive acceleration. And then when we're traveling in this direction here, we're suddenly being pulled or yanked back in the opposite direction. And you don't feel that on a roundabout. When you're on a roundabout, you don't feel that you're being dragged one side of the roundabout in one direction and then yanked back suddenly and have this constant back and forth. You don't feel it. The force you feel is a very, very constant force. You'll feel the force, but you will feel it there constantly all the time. I have never been on a roundabout in my life where I feel like I'm being pulled to the left and then yanked to the right. It just doesn't happen. It's not what we experience. Now let's take the Manchester Ring Road. I dare say that I can get in my car, and if there was no other cars on that motorway, I could travel 100, 110, 120 miles an hour around that ring road over and over and over until I ran out of petrol, and I'd feel fine. I wouldn't feel as if I was being pushed towards one side of the car or pushed towards another side of the car just because I happened to be travelling in a circle. I think I'd feel quite comfortable. But I don't think I could travel even at 15 miles an hour around and around this mini roundabout here without feeling a force, feeling myself being pushed into that car door as I'm trying to go around that roundabout. So I think we can all imagine what I'm talking about here. There are definitely two things at play. We have the speed and we have the radius. If I was travelling at 1 mile an hour around that mini roundabout, I wouldn't feel any force. I'd feel fine. If I was travelling at 1,000,000 miles an hour around the ring road, I'm pretty sure that as I turn the corner, I'd be thrust into the door of the car. So while I agree with you that angular velocity and linear speed are different things, and I agree with you that the speed that we are travelling at is going to affect how much we feel when we're turning a corner, we also have to accept that the radius of that corner, the radius of that circle, is massively important. And that is all angular velocity is. It's a ratio. It is the linear speed we are travelling at divided by the radius of that circle. Angular velocity takes into account both of those things. And we can't ignore either. I am not ignoring the linear speed. I am not ignoring these great speeds that we're moving at. But you can also not ignore the radius of the Earth itself. And the angular speed, the angular velocity, when we calculate it, is tiny. Now remember the train from earlier on. What we don't feel is just linear velocity alone. That plane sat on that train that's travelling at 100 miles an hour will not feel as if it's travelling at 100 miles an hour. It will not feel anything. What we feel is the change of direction when we are travelling at speed. We feel the acceleration. And that acceleration, that rate of change of direction, how fast we're turning, is just far, far smaller when we're going around something big like this compared to going around something small like that. That is what your everyday experiences tell you. So the take-home points from this are, number one, angular velocity does not ignore linear speed. Linear speed is a hugely key component in calculating angular velocity. Number two, acceleration in a circle is felt at every single point around that circle. It's not a case that you're being pulled in one direction at the top and then yanked in another at the bottom. You are feeling that change of direction at every single instantaneous point, and that force, therefore, we feel it as a constant force. And thirdly, that force we feel, just like angular velocity, is also dependent upon the actual speed and the radius of the circle. Now, this kind of physics is done all over the world by engineers on a daily basis. We need it for drills, we need it for machines, we need it for engines, we need it all over the place. And these calculations need to be done, and they need to be done accurately, and they are done accurately. Things do work based on these calculations. Now, ultimately, when we take these calculations that we know work in the real world, the acceleration that we should feel due to the spin of the Earth at the equator, where it should be the greatest, is still only 0.03 meters per second squared. Now, that 0.03 meters per second squared is obviously tiny to the acceleration that we observe when things fall, so no wonder we don't feel it. Anyway, Mark, it was a pleasure to have you on. I hope you've managed to make it through this video, and I would love to have you back on the channel for you to tell me what you think about the way I've addressed your 3 points. Have I changed your mind on anything? Have I driven you further into the flat Earth? Come on and let me know, and have your right to a bit of a response with that. Everyone else who's watching, thank you for watching, and I'll see you soon.